Hi everybody, I hope you can hear me okay. I am about to start the Addictive Brain live Q&A. We're going to be talking things like supernova remnants, which are exploded stars. We're going to be talking about things like black holes. We're going to be talking about the Chandra X Observatory, which is my favorite observatory, and hopefully answering some of the questions that you've had to ask. So a couple caveats. One, this is the first time I've done a live session without anyone helping. So if I mess up, you'll have to forgive me. And number two is I just worked a full day for the Chandra X Observatory. So, if I start missing words or slurring, it's just a little fatigue. It's no big deal. So I thought I would start just with an introduction. My name is Kim Arcand, and I am the visualization and emerging tech lead for NASA's Chandra X Observatory. I think probably a lot of people on this chat session are familiar with the Hubble Space Telescope. The Hubble Space Telescope is kind of like a sister telescope to the Chandra X Observatory. Hubble looks mostly in visible light, as well as some infrared and ultraviolet light. The Chandra X Observatory looks at our universe in X-ray light, just like the name implies. So what creates things that create X-rays, you might ask? Well, we're thinking things like exploding stars, black holes, merging and colliding galaxies, clusters of galaxies, and then also things a little closer by as well, stellar nurseries, and even some objects in the solar system. So there's actually a lot of objects in the cosmos that can create X-rays. So my background is actually in molecular biology is where I started out, and then I went into computer science before essentially getting hired for the Chandra X Observatory. So my background is a little unique. I actually found that the combination of physics and computer science in my background was a really good combination of skills that the Chandra X Observatory could use. And that has led me to working for Chandra for about 21 years. So I'm actually wearing a brand new necklace. I don't know if you can see it. Can you see that? That's actually a really tiny 3D version of the Chandra X Observatory in silver. I just got it on Etsy and I splurged a little because it is the Chandra X Observatory's 20th birthday coming up this July. Chandra was launched on July 23rd and is much bigger than this necklace would lead you to believe. Chandra is about the size of a school bus, and it was launched on Space Shuttle Columbia, and it was actually the largest payload to ever fit in the space shuttle. So that was kind of a cool thing. What's also interesting about Chandra's launch was that being so heavy, it was actually kind of a dangerous mission, if you will, or more dangerous than a mission that would be lighter, for example, in that when you have a very heavy payload, your scenarios for aborting your mission and surviving intact just are reduced. So those scenarios had to be practiced a lot. And the astronauts that actually launched the Chandra X Observatory trained really hard. It was the first mission that was actually commanded by a woman, and Colonel Eileen Collins was the woman that actually led the Chandra X Observatory's STS-93 mission back in 1999. And when you ask Eileen about how they trained, she just talks about how well they knew the material inside and out and how much faith they had in the controllers on the ground, the flight ops crews, and all of the people that would be taking care of them while they're on the mission. And fortunately, Chandra was a successful mission and everything just went very swimmingly. So I am going to start looking at a few questions. If I can do this and multitask at the same time, I might have to put down my phone. So let me know if you have questions. I'll talk a little bit more about what I do, and then perhaps we can start talking about some space stuff. So what I really like about my job is that I get to essentially take data of the universe and do something really cool with it, whether that's create an image or whether that's create a 3D model or whether that's creating a virtual reality application. And sometimes I get to do 3D prints, so I have some here. I get to create things like this. This is a 3D print of a 3D model of supernova 1987A. It's really beautiful because when you look at this object from our point of view here on Earth, it kind of just looks like this donut, kind of plain. But then as soon as you understand the dimensionality of this object and you can look at it from other perspectives, you can see how incredible this object really is. And it also, I think, would make for a really cool bracelet. So if anyone wants to work on that with me, please let me know. I also get to create 3D prints of things like this. This is another one of my favorite objects. This is called Cassiopeia A. This is the remains of a star that exploded, so another supernova remnant. This one is about 10,000 light years away from us, and all the colors that you're seeing here, they actually all represent different colors, representing various chemical emissions. So iron, silicon, sulfur, argon, neon, etc. And those are the colors that you're getting to see. So this is probably one of the coolest projects I think I've ever gotten the chance to work on. And once you have a model in 3D, the amount of things that you can do with that model are pretty incredible. You can bring it into augmented reality, you can bring it into virtual reality, you can do interactive versions like on a desktop. It's just a whole lot of fun. So that's probably like my favorite type of work that I get to do, working with 3D models. And any other kind of data visualization I just find really enjoyable and just really exciting because there's just always something new. I think I will talk just a little bit more about what I do and then start taking questions. There's a couple questions that popped up about black holes. Again, the type of work that I do is more in the data visualization angle of astronomy, but I'm really happy to answer questions as far as I can. And honestly, I'll be very truthful. If I can't answer a question, I will let you know. So ask away. I'm just going to talk briefly about the type of processing we do. So when you're working in X-ray astronomy, the X-ray photons, those little packets of light or packets of energy that we get to look at, they are fewer and far between in the universe than, say, optical light would be. So you have to get, I think, a little bit more creative with the technology that you build to capture those X-ray photons. And you also have to get creative on how you visualize that X-ray information. So when you're looking at an image of an object in X-ray light, it doesn't often look like some of the more stereotypical images that you might think of from, say, the Hubble Space Telescope. One of the things that I find is a successful technique to help fix that is to combine the X-ray light with another kind of light, such as optical lights or perhaps infrared lights or ultraviolets, radio, you name it. And this technique is really useful because not only does it help demonstrate the object better, but it also often helps underscore the sort of complexity of that object and the importance of multi-wavelength investigations of things in the universe. Because, if we could only see the universe in one kind of light, like for example, the kind of light that our eyes can detect, we'd be missing out on a whole lot of data. So being able to look at the universe in many kind of light, it's like having just a whole lot of tools in your tool belt as an astronomer. Being able to look at things like exploding stars or black holes, galaxies, clusters of galaxies, stars that are being born, stars that are on their way out, having all of those different kinds of light to look at those different kinds of objects just gives you more information. It helps add to the information of your image, of your data set overall. And another thing that I like to mention briefly is that these images of the universe, they're not these giant space selfies. It's not just a point and click kind of process. It truly is a process of translation, of taking that data and creating the visual representation of that object. Because when you're using telescopes such as Hubble, such as Chandra, such as other ones that are on the ground, you are magnifying that light and you are essentially giving us like superhuman vision, if you will. These are things that we can't really see with our own eyes typically, especially when you're in the X-ray regime. You can't see any of that light at all. But even a lot of the images that the Hubble Space Telescope takes in optical light, say, the magnification process of that data, right? That alone gives you something that our sad, puny eyes, as awesome as they are, can't really do for us. So it's all a process of translation, creating that information, and then being able to make that visual representation. And one of my favorite steps of that process is actually adding the color at the end, because this information, if we're looking at an image in X-ray light, there's no true color in like the human eye or value of color as we're kind of used to it. So we have to add that information, kind of like you would add color information to a weather map on your weather app or on the nightly news, right? If you're looking at a map of precipitation or wind speed or temperature, those maps are typically color coded in some way so that you have a very simple visual cue to look at that information and to get a better sense of what's happening in that object. So we do the same thing with astronomical objects. We apply color as a way to add to the overall information quotient, which I think is actually a really cool part. So I'm gonna put my phone down so I can have my hands back, and hopefully I'm borrowing my daughter's little penguin beanie bag to do that, so hopefully this will stay. And I'm gonna try to hook it down so I can be hands free for a bit. Let's see if that works. Did that work? Stay. Okay. So I think we had a couple questions come up about black holes, but I have multiple windows going, so I'm going to be looking over here to see what some of these questions were from earlier in the day. All right, so the first question is about indeed a black hole. So what is a black hole, and are we going to die by black hole? Well, I'm all about stellar death. I love talking about that, so no judgment from me here. If you're a little on the darker side, but I can definitely talk a bit about black holes. I think black holes are really cool objects to talk about because they really capture the imagination. So a black hole essentially is a super ultra dense region in space where the gravitational pull is so strong that nothing, not even light, can escape from that object. One of my favorite black hole resources, actually maybe I'll pick up my phone and show you. Can I turn this around? Let me try this. No, that didn't seem to work. No, that didn't work. All right, well, let me see if I can do it this way. No. Okay. So I don't know if you can see very well, but essentially this is one of my favorite black hole websites, and I'm very biased because it's on the Chandra website. So it's chandra.si.edu/black hole. And it just has a number of recent discoveries and descriptions on what black holes happen to be. It's got some of the basics like an anatomy, the anatomy of a black hole, the accretion disk, the event horizon, the jets, the singularity. And then it talks a little bit more about some of the really cool findings that Chandra has been able to find, as well as a really thorough question and answer kind of session. So black holes are just really amazing objects because if you think about it, if a black hole is a point where light cannot escape, we can't see these objects directly, right? So there's a lot of math involved and really a lot of awesome technology in being able to develop the tools and technology that we need to see these black holes, meaning to observe them in some way. We can never observe a black hole itself directly because, as the definition implies, light cannot escape. However, we can see areas around them. And what's really great, probably a number of you are familiar with the recent press release that came out from the Event Horizon Telescope, and that was the first ever image of a black hole. A really good description of that is that it's an image of the silhouette of a black hole or perhaps a black hole shadow, but it's probably like the best we can do. And to be honest, that results, when it came out, like I felt like I drank like 10 cups of coffee that day when that result came out. I was so excited. Never, like in my lifetime, had I thought that I would get to see that kind of visualization because it just seems so sci-fi, so incredible. that we would ever be able to build the equipment needed to do that kind of imaging power. So just to talk a little bit about the specifics, in order to image a black hole like the one that the EHT, the Event Horizon Telescope, imaged, which was pretty far away. It was in the galaxy M87, which, I don't know, it was like, what, 60 million light years away. I mean, it was pretty far. And to have the kind of resolving power to do that, you essentially had to turn something the size of the Earth into a telescope, right? Now, to build a telescope the size of the Earth would make it too big and heavy, and it would essentially like collapse under its own weight. So how do you do that? How do you create that resolving power when you can't build something that big? And Shep Dolman, who was the head of the project and one of the driving forces behind it, came up with this great idea to essentially take the Earth and create a sort of virtual observatory, if you will, by combining multiple radio telescopes on the Earth in such a pattern that when they're all looking at the same object at exactly the same time, like down to such an incredible specific degree, that then you could use that combined resolution and then do some very sophisticated imaging techniques using amazing software in order to get that image. And I mean, this was, a couple decades worth of work, essentially. And to be able to see that resulting image in my lifetime, I mean, when I started doing this 20 years ago, it's just not something I ever would have expected to see. So yeah, that was kind of like the highlight of the year. So I'm seeing questions go by. So that was one question. So black hole, I think I answered. Oh, but the second part of that question was, are we going to die by black hole? So no, we shouldn't die by black hole, at least not that I'm aware of. Here's the thing. I think black holes kind of get a bad reputation. I think they have this reputation of being like these giant cosmic vacuum cleaners. People get the idea that they're just kind of going around space, going around the universe, sucking things up like a giant cosmic Roomba or something, right? And I feel like that would be a great commercial for Roombas. But anyways, I should say I do not endorse any commercial products. So anyways, but they're not. They think they don't suck things up, right? So essentially things fall into them. So there's no black hole like in our solar system zooming around sucking stuff up, because A, black holes don't do that, and B, we don't have any in our solar system. So even if we say took our sun and magically bibbity boppity booped it into a black hole, that black hole would be pretty small, relatively speaking, and Earth would just continue to orbit around that black hole as if it were no big deal. However, without our sun, without light, which we need to survive, we'd eventually die. So yeah, I guess we could die by black hole, sort of, if we turned our sun into one, which we can't. So anyways, great question. I love that question. The other question that we got earlier today was, what is the temperature of a black hole and how do you measure it? That's also great. Now, I actually find this stuff really confusing. Once you start talking about like what's inside a black hole, it's just crazy to think about. Like, it blows my mind, figuratively speaking. So let's just say that when we're talking about black holes, I love to talk about how hot they are around the black holes, because essentially the way we get to see X-ray results of, say, a black hole is because we are seeing, say, material around a accretion disk, right? So as material is falling towards that black hole, there's that gravitational pull. This gravitational pull creates essentially an accretion disk, if you will. And that disk of material is really hot. So we can detect X-rays from something like that, but that's not a detection of heat, say, or high energy from the black hole itself, because again, we can't see black holes directly. However, Stephen Hawking figured out quite a while ago this concept of Hawking radiation, that black holes themselves, the objects, are actually pretty cold. And I think what's interesting about it is that that temperature is sort of inversely proportional to the mass of the black hole. So, for example, you can say that a very supermassive black hole will actually be really cold, like close to absolute zero, though not exactly at absolute zero. So a supermassive black hole is something with millions or billions of masses of suns in it. When you're talking about a smaller black hole, like a stellar mass black hole, that's also going to be really, really cold, but not to the level of absolute zero. So I've always thought that's kind of a cool thing, that, not pun intended. So black holes are really cold, but the material around black holes are actually incredibly hot. And I kind of love that juxtaposition of the hot and the cold. And I guess just to follow up on the death question, death by black hole, I mean, if we did ever fall into a black hole, which would be, not cool, you would definitely not survive that. You would be like, I think the word is spaghettified. Essentially, you're just kind of stretched thinner and thinner and thinner until you're essentially molecular spaghetti, which I'm pretty sure, it's been a while since I was in biology class, but I'm pretty sure humans could not survive spaghettification. So death by black hole would not be cool at all. Okay, so those are the two questions that I got earlier. I'm gonna wave at a couple people because I will feel like I'm a little bit more technologically cool if I do that. Awesome. Ooh, maybe I'll put a filter on. Should we do a filter? Ooh, no, I don't like that. That makes me look weird. All right, let's try a different one. Ooh, maybe this one would be fun. No, I don't like that either. Oh, that's weird. Ooh, sunglasses? No. No. Ooh, I like that one. How about this one? Ooh, that's fun. Okay, so spaghettification, yes. Isn't that a cool word? I agree. That's really awesome. So I think I saw earlier a question go back on visual representation of the object and how we were talking about that. Oh, this one has moons or something in it. That's fun. Oh, Ramadan. Cool. So yeah, I think talking about visual representation is really interesting to me because, again, these are objects that you can't, see with your own eyes. So when you're dealing with something like X-ray light, or any kind of light, really, you're creating this object through this process of translation, as I mentioned. So it's not a perfect selfie. You actually have to do this translation using software. So, for example, if the Trandrax Observatory is looking at an object, say 10,000 light years away, and that object happens to be Cassiopeia A, my BFF, this supernova remnant, that information has been traveling across the universe, right? And it's observed and recorded on the detectors and packaged up in the form of ones and zeros, sent down to Earth through NASA's Deep Space Network before eventually it gets to, say, my laptop or someone else's laptop. Once it's there, you have to kind of unpack it and then translate it. So you might start off with, you could start off the very first with binary code, which is the way it's encoded. And then binary code is just a system of ones and zeros or ons and offs. Then you use scientific software to translate that information into like a table. So you would have the position of each photon, each packet of energy that struck the detector, X, Y, and coordinates. Then you would have the time and the energy, say, of each of those photons that struck the detector. And then you're going to use that information to create the visual representation of the object using more software. So it really is a process of translation and transcription. It's the idea of that, however, is two things I think to keep in mind. One is that these images of the universe are creations by people. So someone like me, I'm doing that process of translation, and obviously I am doing it according to the science. I'm trying to tell the story of the science data, but I'm still a person, and I still have, my own biases and my own viewpoints and my own point of view, aesthetically speaking. So if I'm creating an image, I've definitely seen patterns in the types of colors that I prefer to help tell the story. Sometimes the data kind of tells me which colors, if you will. I know that sounds weird, but I can usually tell which direction we need to go on based on the type of data, the type of information that I have to work with, and I kind of know which colors will work really well to help tell that story, but it's still a process of figuring it out and just seeing what works. There's definitely some trial and error involved, and I think what's interesting to note is that, no matter how much you try to make this objective, there's always going to be quite a bit of the image creator, the scientist, the astronomer, whoever is making it, their bias and their perspectives on things. So yeah, so that was a great question. I see another person loves spaghettification. I'm going to wave a couple more. Ooh, that's a fun filter. I'm just going to keep changing filters while I figure this stuff out. So, all right. How am I? I'm doing great. How are you? Is the radio telescope image from the black hole something we could optically see? So not exactly. The mechanism for looking at that type of image, it's just that it's like best to look at in certain kinds of light. So radio telescopes and X-ray telescopes are really important tools for looking at things like black holes. Opposites on the electromagnetic spectrum, radio's over here, X-rays are over here, but both really important tools and highly complementary, by the way. So X-ray and radio combinations are probably perhaps some of my favorite, as my friend Summer Ash knows if she's on here. The idea that two opposites on the spectrum can be so good together, I think is really kind of cool. When you're looking at something like a black hole or the area around a black hole, you want to use the tools that are best going to showcase that data. And if you have a tool like Chandra, what you're looking at is essentially the farther out region of that black hole. So you're going to be looking at, say, a large jet coming out of the black hole, and that jet could probably stream for like 1,000 light years. Just for anyone who doesn't know, a light year is essentially the distance that light travels in a year, which is about 10 trillion kilometers, give or take. I'm rounding numbers, but approximately. So if you picture a 1,000 light year jet, so 1,000 times 10 trillion kilometers, and that tells you how long it is. So Chandra is great to look at things like that, and what jets will tell you is how that black hole is interacting with its host galaxy, and sometimes even further out. Probably one of my most favorite results from Chandra and other telescopes goes back to, I want to say 2007 maybe, or maybe it was 2000. I think it was 2007. It was 3C321, which was nicknamed the Death Star Galaxy. It was this supermassive black hole in a galaxy far, far away. And yes, I love Star Wars, so this is like why it's one of my favorites. And this black hole had a massive jet of high energy particles streaking out of it, so big, so massive, so energetic that it was streaking out into beyond the galaxy itself, beyond the host galaxy, and into another smaller galaxy nearby and disrupting that smaller galaxy. So this jet of high energy particles was essentially, well, I wouldn't say obliterating, but doing some damage to possible stars, planets, perhaps, in that other smaller galaxy. And that's why it was nicknamed the Death Star Galaxy, because it was kind of like the Death Star on Star Wars, and, the beam of material that comes out. And anyways, I thought that was a really cool thing, and much better to name it the Death Star Galaxy than 3C321, which is boring. So anyways, I love black holes because I think, again, I talked earlier about how this idea that black holes are just giant cosmic vacuum cleaners is not true. There's also this idea that they're just massively destructive, and while they certainly can be destructive, that example I just gave you, it's not cool for the planets that it could perhaps be messing up. However, black holes are also kind of responsible for the care and feeding of galaxies, and that's something that's been really cool to see since Chandra was launched 20 years ago, seeing all of the incredible data on black holes and what we've been able to learn from it, from telescopes like Chandra, from radio telescopes, from the NRAO, from the Hubble Space Telescope, from Spitzer. All of this armada of telescopes have been contributing to our knowledge of black holes. And it turns out that black holes are cool for the sort of care and feeding of their galaxies, but they're also kind of like giant cosmic recycling centers. So black holes are actually pretty important. Our black hole at the center of the Milky Way galaxy, Sagittarius A star, that black hole is a little bit quieter than, say, the one in M87 that the EHT looked at. And I think that's probably good for us, because that means we're just in a great spot in this, spiral galaxy. We're in a cool little corner, and our black hole is burping, yes, but not massively feeding and not massively energetic like the one in M87 is doing. So I think that's pretty good for us. But it is really interesting to think about how black holes can contribute to this kind of process of cosmic recycling, and also to this idea of the care and feeding of its host galaxy. So, all right, I hope I answered your question. Any more questions here? Hi, Kimberly. I saw a video where you were using VR, virtual reality, for visualization. Is that work on display at a particular venue, or is it still in development? Thank you for asking that question. This is one of my favorite things to talk about too. So virtual reality is something relatively new for me. I think I mentioned that I have these great 3D models that we've been able to work with at the Chandrax Observatory, and that's really fun. But once you have a 3D model, the sort of things you can do with it are innumerable, right? So one of the things that we can do is to take that 3D model and then create a virtual reality application, or an augmented reality application, or mixed reality, whatever you want to call it. And what we were able to do with this 3D model, Cassiopeia A, and also this 3D model of supernova 1987A, is to turn them into virtual reality. So a quick story there, if people don't mind the little story, is that a couple years ago I wandered into a visualization lab at Brown University, and it was a 3D lab called a yurt, which means there's like 60 cameras strung around the ceiling, and you're in this round immersive space, and you wear a headset, and then the entire room is transformed into a 3D virtual environment. And some of the things that we looked at, it was just like a little field trip I was on with some local high school students that I was mentoring. And some of the objects that we got to look at were like dinosaur footprints, which was pretty cool, and a 3D heart, which was awesome because I used to really be interested in medicine. And then the third one was essentially this great 3D view of Mount Sharp on Mars, taken by Curiosity and I think another telescope or two. And so essentially I got to walk on Mars, on a part of Mars that I had looked at many times. So when I talk about data visualization, I use this idea of Mars images and why we have to color code those images a certain way to help scientists and geologists here on Earth understand the data. So it was an area that I was pretty familiar with. And being able to walk on it and experience it in 3D was just incredible. And I thought to myself, like, well, if we can do that from Mars, surely we can take this 3D model of Cassiopeia A, this supernova remnant, and turn that into virtual reality. And the lab manager of the yurt, Tom Seguros at Brown, was like, yeah, sure. So he was great, totally good sport. And I sent my 3D data down, and we worked with some students to translate that into virtual reality. And essentially I got to walk inside this dead star, this star that exploded 10,000 light years away from us. So 10,000 times 10 trillion kilometers. The mass of Cassiopeia A looks really small because, right, I can hold a version of it in my hand. This is like maybe 4.5 inches across. But that object in real life is about 40 million billion times the surface area of our sun and planets, and you can toss in Pluto, whatever, if you're into Pluto. And so the idea that you could walk inside this object and see it in a very different way and experience it in a very different way was incredibly inspiring. So we worked with a few other students to create a version that you could use on personal virtual reality devices such as Oculus Go's, or Oculus Rifts, or even Google Cardboard. And that application is still in beta. So as a computer scientist, I would keep things in beta forever if I'm allowed. but I try not to. So yes, if you have access to VR equipment, I can give you the URL. It's chandra.si.edu/VR. And I believe one of the versions of that application are on the website. If you are interested in a different version for a different kind of equipment, just send me an email. My email is on that website. It's chandra.si.edu/VR, as in virtual reality. So you too can walk inside an exploded star and get to experience all of that material and see how the coating of the iron versus the silicon versus the sulfur versus the calcium, see how that plays out. And what I think is really interesting for that type of project is that when you're looking at a supernova remnant, a star that's exploded, and you're seeing it in this three-dimensional way, you can clearly see that the iron is on the perimeter of that object. So looking at this model, the iron is color-coded like black here, so you can see it's on the outside. Now, when a star is getting ready to explode, the iron is actually in the core of the star. So how does the iron that was once in the core make its way all the way to the outer perimeter, right? Isn't that a great puzzle? I think it is. And there's a couple possibilities. So we don't really know. Scientists aren't really sure exactly how stars explode and how they turn themselves inside out when they do, or when some turn themselves inside out when they do. But it's possible that the material inside the star is mixed right before explosion, or it's possible that something happens in the explosion. I don't know. I think it's an amazing puzzle. And one of the things that I like best about astronomy and why I've worked in it for 2 decades is because every time you answer a question or think you're going to answer a question, you get 10 more questions to find the answers to, and it just grows exponentially. So you never really know anything, and I find that really refreshing and exciting and stimulating. So you can never get bored in astronomy, that's for sure. Okay, so fascinating. Thank you. I'll check it out. All right, thank you. I'm glad that actually helped answer your question. So I'm not sure. It's about 37 minutes, and I think the questions have kind of slowed down. So if there's anything else, I'll stick on for another minute or two. Any final questions, please add it below so I can see it. And yeah, it doesn't look like I missed any others. All right. So I guess that's it. I'll just say this was fun. Hopefully you didn't mind my shaky camera view, because the perspective from it being down here was just really weird. But whatever, this is Instagram, and I think it's supposed to be kind of casual. So if there's no questions, I'm just gonna say wave, 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 wave. Hopefully I've waved to everybody. Thanks for spending some time with me today. I hope you enjoyed everything, and hope you didn't mind the experiment as I kind of figured this stuff out. So yeah, I'll talk to you soon. I'll just say the universe is yours to discover, so have at it. Bye everyone.